This video covers current. Now first off, we need to look at the motion of charges in a circuit. We know from electrostatics that the charge carriers are the electrons. They're the ones that are actually doing the moving. We said that protons themselves can actually not move. So, the motion of charges are caused by a potential difference. Again, we saw this with electric potential. That this potential difference causes electrons to move from low to high potential. Now, because electrons and protons have the same charge, so the charge of an electron is equal to the charge of a proton, then it doesn't really matter which one we look at. Conventionally, we're going to treat as if the protons are the ones that actually do the moving. So we've seen this symbol before. This is a battery, where a long piece is a positive side and the short piece is a negative side. So if we're looking at a circuit, we're going to say that the direction of the current is from the positive to the negative. Now, as these charges move, they actually start colliding with one another and with imperfections in the wire. These collisions slow the charges to a very slow speed, and we're going to look at what that speed is next. So here we're looking at current and drift velocity. Remember, we said that the flow of charge is some charge per unit of time. This is going to be known as current with a variable I. It's going to have units of amperes. We're going to say amps for short. So let's say that we have a current in a circuit that's 2 amps, then that's current equal to 2 amps. So our current is also going to be equal to this equation here, capital N times E times V times A, where N is the number of charge carriers per volume. That means charges per meters cubed. E is the charge of an electron. Again, this is just a magnitude, 1.6 times 10 to the negative 19. And V is the average velocity of the charges attained due to an electric field. Remember that an electric field is produced by a positive and a negative plate charge, in this case, a battery. So it's going to create a potential difference between that battery, and that electric field is going to cause charges to move. Also, A is equal to the area of the wire. So we're going to derive another equation. If we start off with I equals N times E times V times D, we can use the definition of N and velocity to expand the above equation. Namely, we said that N is the number of charges per unit of volume, so we can replace that here. Again, we know that velocity is distance over time. Now, by multiplying the number of charges by the charge of an electron, E, we get the total charge. We saw this in our very first electrostatics, that Q is equal to N, or little n, times E. Okay, that our total charge is equal to the number of electrons times the charge of one electron. In this case, our distance in the x direction is going to be the length that our charges move in that direction. So we're going to replace delta x with L. And then finally, we know that the area times length of a cylinder is its volume. So we can replace volume with area times length. And you'll see that these L's and A's will cancel out. And all we're left with is this final equation. Current is equal to charge per unit of time. Now, the reason we derive that equation is because it only works for a constant current flowing with a constant average drift velocity. Real currents accelerate up to the drift velocity when a circuit is turned on and then decelerate when turned off. The following formula is useful when the current has not yet reached a steady state, or constant average drift velocity. So that means we need to use other equations when we are looking at the very beginning or the very end of our circuit, of our current. Namely, we can use current, I, is equal to dq over dt, which means that we can also write this in terms of an integral. Now, you don't have to use these equations if you're asked for instantaneous current, or if the circuit has been running for a long time or has reached a steady state. And we'll see examples of all this later. Finally, we're going to extend our equation I equals NEVA one last time. So what we're talking about now is current density. If current is I, and we said normally that density in this case is going to be current per unit area, then we can simplify this equation to its another form that we also use, where J is equal to our current density, and that's equal to N times E times V. So again, just another version of this equation. Also, it's important to remember that N is not just the number of charges, but it is the number of charges per meter cubed. Also, N is usually known for various materials. So for the most part, it's not going to be something that you solve for. It's going to be given information and you're going to use it to help you solve for other things. So let's look at this first example. It says that we have 12.5 times 10 to the fourth electrons that flow through a copper wire with a diameter of 8 millimeters in 10 seconds. And we're asked to determine the drift speed of the charges. So first off, we want to label all of our information. So this 12.5 times 10 to the 24 electrons, that is little n, that is not capital N. This is the number of electrons that flow through a copper wire. And the N value for copper is 8.85 times 10 to the 28. Again, for the most part, that's information you're just going to receive. Here, we're given a diameter of 8 millimeters. So that's a radius of 4 millimeters, or 0.004 meters. And time is given to us in seconds. And we're asked to solve for the drift speed of the charges. Now again, for the most part, some of this information is not necessarily useful in the way that it's given to us. Again, this 12.5 times 10 to the 4 electrons needs to be converted into charges. So our total charge Q is equal to 12.5 times 10 to the 24th electrons times the number of electrons, or the charge per electron. Again, that gives us a total charge of 2 times 10 to the 6th coulombs. Also, that radius, again, not useful in the way that it's given because normally we need area. In this case, wire is normally a cylinder. So our area will be pi r squared for the ends of that wire. So that's pi times 0.004 squared. And we get 5.02 times 10 to the negative 5 meters squared. And then finally, we're asked to solve for our drift speed. So we can use the equation I equals NEVDA. And we can replace our current with our charge per unit of time. So a little algebra. And we get, plugging in all of our numbers, we should get a velocity of 0.29 meters per second. In this example, we have 20 coulombs of charge that move past a point in a wire in 40 seconds. So 20 coulombs is our charge, Q, 40 seconds is our time, and we're asked to solve for the current. So that's 20 divided by 40, or Q over T, gives us 0.5 0.5 amps. Now you're also asked to determine the number of electrons that move through that point each second. So if 0.5 coulombs per second, and again a coulomb was our charge, seconds was our time, so coulombs per second are equal to amps. So if we have 0.5 charges that pass every second, and 1.6 times 10 to the negative 19 coulombs is the charge for one electron, that means that 3.125 times 10 to the 18th power electrons pass per second. In this problem, we have the amount of charge passing through a wire is described by the function Q is equal to 3t cubed plus 4t squared plus t plus 2. And we're asked to determine the current. Well, we said that the current is equal to dq over dt. So we need to take the derivative of it and then evaluate this equation at 2 seconds. So the derivative of 3t cubed plus 4t squared plus t plus 2 is just 9t squared plus 8t plus 1 and then plus 0. So this is our function for current, and now we're going to evaluate this function at t is equal to 2 seconds. And you should get a current of 53 amps. In this example, we have a current at time t that's described by this function I is equal to I naught e to the negative t over tau, where tau is a time constant measured in seconds. The initial current in the circuit is I naught equal to 2 amps, and we're asked to determine the current in the circuit when time t is equal to tau. So, when t is equal to tau, we can plug that in for t. These taus are going to cancel out, and I have I naught, which is 2, times e to the negative 1 power, which is 0.735. So this is our current when t is equal to tau. Now we're going to do the same thing when time is equal to 10 times tau. So we go ahead and substitute that in. Again, my taus cancel, and I'm left with 2, which is my initial current, times e to the negative 10 power, which gives us 9.1 times 10 to the negative 5 amps. So you can see as time increases, my current starts to decrease dramatically. So what happens if we put time equal to infinity? Well, if we put time equal to infinity times tau, our taus will still cancel, and e to the negative infinity power gives us 0. So our current will just be equal to 0. And you can try putting those numbers into the calculator. As a multiple of tau starts getting larger and larger, this entire piece starts getting smaller and smaller. So again, you can try putting those numbers in the calculator, and you can see that for yourself. In this final example, we're asked to determine an equation for the amount of charge, not to be confused with I, charge is Q, at a time t. So that means that our charge, which is equal to the integral of current with respect to time, is what we're being asked to solve for. So we can substitute in our current equation. For what we have, and again, we're taking this integral with respect to time. So we only have one variable t in here. So what I'm going to do is called u substitution. You should have seen this in your calculus class, where u is going to be equal to negative t over tau, which again is just negative 1 over tau times t. And then I'm going to take the derivative of that with respect to t. Well, the derivative of this is just negative 1 over tau dt. Because again, tau is a constant here. So what I'm going to do is I'm going to rearrange this to get negative tau du equals to dt. So now what I'm going to do is the substitution part. Wherever I see a dt, I'm going to replace it with this portion. And then wherever I see a negative t over tau, I'm going to replace it with a u. So that means that my function, or my integral, now looks like I naught, which is just a constant, so I could have actually pulled that out of my integral, e to the u, and then I'm going to replace the dt part with negative tau du. So I'm going to go ahead and take out all my constants so this looks a little cleaner. Again, you've seen this equation before. The integral of eu is simply just eu. So I get I naught negative tau eu as my integral. Now I can go ahead and just go back and replace u with my, that's a tau. I can go ahead and replace it with negative t over tau again, because that's, again, what it was to begin with. And I'm going to evaluate this function from 0 to time is equal to t. So when I evaluate this function, I get I naught negative tau e to the negative t over tau minus a negative, I'm going to go ahead and pull that negative to the front, I naught tau e to the 0 over tau. Now you need to be careful because e to the 0 power is just 1. It's not 0. So I can pull out all my common functions or common variables here. And I'm left with negative e to the negative t over tau plus 1. Or normally this is written as 1 minus e to the negative t over tau. Now we're going to see this equation again, so make sure that you're comfortable with the derivation of it.